I guess it's time to start. I'm very happy to announce Junliang Shen from Yale University, and he will tell us about motives of the Hitchin system.
Okay, thanks. Yeah, it's great to be at Princeton at this pleasant weather. So I'm going to talk about, and also this is my first time to be speaking at the Institute, so it's my great honor. So I'm going to talk about the motives of the Hitchin system. So everything in this talk is in joint work with Davesh, Maulik, and Qizheng. Okay, so let me start with an overview of what's going to happen. So in the purpose of this talk is to explain the connection of two different structures. On one side is the symmetries. Let me be vague at the beginning, and I will explain precisely what's the meaning of it later. So the symmetry of the derived categories of coherent sheaves on varieties, and this is the one side of the structures we're interested in, and the other side is the cohomological structure, the structure of the cohomology or chow of that variety, those varieties. So the connection. So this seems to be two very different structures. So derived category of bounded derived category of coherent sheaves, and this connection is by considering the fancy words motives, or more precisely, you can. So the easiest way to see that there might be a connection of these two structures is that once you have symmetries of the derived category of coherent sheaves, you know that they are given by Fourier-Mukai transforms. So which will give you interesting K-theory classes over the varieties, and then you can obtain algebraic cycles which act on the cohomology or chow or even K-theory of these varieties and operator, and this symmetry usually will imply interesting results. So one of the very few to construct algebraic cycles from the symmetries of the derived category of coherent sheaves. So one of the first examples which this kind of phenomenon was illustrated was the case of abelian schemes. So if we consider the abelian scheme over some base, say B, and then one of the very famous symmetries of the derived category of coherent sheaf is given by Mukai, so which is now called the Fourier-Mukai transform. So this is Mukai's transform, which connects the dB co of A with the dB co of a dual, the dual of the abelian scheme. But on the other side, so the cohomologically and the chow, this is actually a motivic lifting of a very classical story here by considering the group structure of the abelian scheme. So you have the abelian scheme, and then you can pick a large n. So this is the multiplication by n map. You scale any point by its nth power, which induces actually an operator on the singular cohomology with rational coefficients. So you have a linear operator of a finite dimensional vector space, so that you can decompose the entire cohomology into wave spaces with respect to this decomposition. So this I from 0 to, well, I just put I here. I, where this I is the I's eigenspace. So you pull back along the multiplication by n. It's given by the weight I. This alpha is the weight I eigenvalue, eigenvector, and so this is so. At the end of the day, we know that this is actually first. This is a decomposition which depends on n, but it turned out that does not depend on n. And moreover, this decomposition is motivic. So as I will explain later, that there is a decomposition of chow motives which realize every piece. And then the corresponding algebraic cycles are given exactly by Mukai's Poincare light bundle. And this is one of the, so this direction was established by O'Neill and Ellinger Moore about 30 years ago. And so the good thing for this geometry is that there's no singular fibers. So the picture is the following. So you have A to B, and every fiber is a torus, it's not abelian variety. Okay. So the purpose of today's talk is to explain it, a version of this for the Hitchin system. Maybe let me start. Let me continue on this blackboard. So now instead of considering abelian variety, we can consider a Hitchin system, which I will introduce in a minute. Which I denote it by F which goes from the modular space of Higgs bundles to some base, and the picture, the cartoon for this Hitchin fibration is that you have generically you have an abelian variety, but over some locus things can be very complicated in an interesting way. So let me first write in the things in so the reason for looking at this connection is that people expect that the dB co of the Hitchin system share a lot of interesting symmetries predicted in mathematics and also physics by geometric. Let me put the quotation marks here, meaning that there are variants of the dB co. So there are symmetries provided by geometric Lagrange and also by S duality. And the cohomology of these modular spaces was also studied intensively over the last few decades, where there are also a lot of structures predicted here. For example, as I will review in a while, so the P equals W phenomenon, the P equals W conjecture, concerning the cohomology of the Hitchin modular spaces and how it interacts with non-abelian Hodge correspondence, and also topological mirror conjecture, originally by Hodge and Thaddeus, and also the connection. This cohomology also underlies certain structures in intuitive geometry called the BPS invariance. So there is a list of cohomological predictions or some of them are proven already concerning the cohomology of the Hitchin modular spaces. And then, so the question is whether there is an arrow like this. So telling us that the symmetries of these coherent categories can tell us an interesting property. And this is the purpose of today's talk. And the answer is partially yes, although a large part of the story there is a large part of the story we haven't completely understood. Okay, so this is an overview of what's going to happen, and let me get into details. Let me start here, maybe. So the first part, so since the purpose is to explain that a large part of the cohomological symmetries for the Hitchin modular spaces are actually motivic, where the corresponding algebraic cycles eventually will come from these symmetries. So let me start with the topological side, the right side of the story. Okay, so for this part, we will work over the complex numbers, and for the Hitchin system in today's talk, there will be the GL and Hitchin system where we will fix two integers n and d to be coprime. So here n will be the rank, and the d will be the degree. We'll fix two integers, and we also can fix a curve or Riemann surface, curve, a projective curve of genus at least 2. So to indicate the independence on the n and d, we use m and d to denote the modular space of stable Higgs bundles, modular of stable Higgs bundles, which are pairs E and theta, where E is a vector bundle of the given rank and degree. And the theta is a Higgs field, which is an endomorphism of the bundle twisted globally by the canonical bundle of the curve. So this is Higgs field. And the stability is with respect to the slope, the rank, sorry, the degree of the bundle over the rank. So you require that every sub-Higgs bundle to have a smaller slope. Okay, so and this space admits an Hitchin system, an integrable system, given by which I will use the FD to denote the dependence on the degree you choose, and the base is only dependent on n, the rank. So the Hitchin vibration is basically given by calculating the characteristic polynomial of a Higgs field. So you have a bundle with an endomorphism, twisted endomorphism, then we can calculate its characteristic polynomial by collecting the coefficient of the trace theta, trace of wedge 2 of theta, and so on, just the determinant of theta. Oh, is this visible? So this clearly will be lying inside the vector space given, a finite space given by C and omega C tensor I, where the corresponding group will, this group will collect the corresponding coefficients, where I goes from 1 to n. Okay, so this is exactly your base. So it is known that FD is proper, it's actually projective, and even it is Lagrangian with respect to a natural homomorphic symplectic form, which I not this is the part of the information I will not use today, but just let me mention this is actually Lagrangian. In particular, this suggests that a general fiber is an abelian variety, and the dimension of the total space is twice the dimension of the base. Okay. Okay, so this is the main character of the Hitchin system, and I will describe 3 results concerning the relative cohomology of the Hitchin space, the Hitchin vibration. So one of the interesting features of the Hitchin vibration is that a generic fiber is just a Jacobian of so a general fiber would be only a Jacobian of a spectral curve, which is an abelian variety, but a special fiber will contain the modular space of vector bundles on the Riemann surface, which is
which just says itself.
Sorry.
The generic fiber is abelian variety.
Generic fiber.
You just said.
No, there's no section because of this D and D co-prime. There's no section.
What did you just say? Something.
A general fiber.
General.
A general fiber is an abelian variety, which is the Jacobian associated with a smooth spectral curve.
Not this curve, different curve.
Yes, different curve. So yeah, so the Bn. Yeah, thanks for the question. So Bn can be thought of the spectral curves which are n to 1 curves which are n to 1 cover over the 0 section which sits inside the T star of C. So the picture is that if you so here the base parameterizes the eigenvalues. So for any point on the C, the eigenvalue there are n points, and then the point varies on C. This you get a curve, and so it's a different curve, and the curve varies when you when the point varies on the Bn. But an interesting point is the point where every component is 0. So then this means that you are considering the Higgs bundles with a trivial characteristic polynomial. So that component contains, for example, the modular space of vector bundles. So this is a space which puts the modular vector bundle and a bunch of abelian varieties together. Yeah, thanks. So the big, yes. Okay, so I want to describe first the three theorems concerning the relative homology of FD, which is basically so the first, of course, is the decomposition theorem by Bayes and Weierstein, and Garber, who tells us that if you consider, so the relative homology is just the push forward of the constant sheaf upstairs. So this is a, so you have a morphism and you push forward the constant sheaf here, and then they told us that this splits into a bunch of semi-simple perverse sheaves. So you have this complex and you take the perverse homology. So to avoid further confusion, let me do the shift slightly wrongly, because it's different by a global shift dependent on the measure of the M and B, but let me write this way. Okay, so this says that the total complex actually can be written as the decomposition of those building blocks of the category of abelian category perverse sheaves, which are semi-simple perverse sheaves. The Hitchin base. This is, of course, it's very helpful in calculations, but still there's also, so in order to decide these things, one has to calculate the supports of these semi-simple perverse sheaves, but also the local system associated with them, which usually is very challenging. However, so the decomposition theorem for the Hitchin, so decomposition theorem is a very general tool in studying the topology of algebraic maps. But for the Hitchin system, there's motivation from other areas which suggest that we take a closer look at the shape of the decomposition theorem. So this was initiated by Ngo, I think around 25 years ago, where he gave a more precise. So not only that you can split things into semi-simple objects, but more precise description of these building blocks, or of the semi-simple perverse sheaf that showed up. For example, if you restrict ourselves to the locus of so the Hitchin base can be thought of the parameter space of the spectral curves. And if we restrict ourselves to the open subset of integral spectral curves, then Ngo actually, his work decide all the pieces that showed up here. So it's the complete information. But this is, let me mention that in general, so when the spectral curve is non-reduced, for example, so where the curve is broken and you have multiplicities, then in general, still not understood, not completely understood. I want to say something about the decomposition theorem, but not completely understood yet. Even, for example, it's not even classified what are all the supports that would show up in the right side. Then, of course, Ngo's motivation comes from his proof of the fundamental lemma. See, of course, he established the description not only for GLN, but also for Engel's work treats the general reductive G, and which deduce the fundamental lemma of the nonlinear program from the study of the topology of the Hitchin vibration. And I guess actually maybe a large part of this work has happened here in the institute probably. Okay, so
sorry, maybe you already explained this to me earlier today, but are the supports pulled back from mg bar, or is that not the case?
mg bar, what do you mean?
Like there's a map from the Hitchin base. Oh
No, it's not stable curves. These are
okay, sorry.
the singularities are worse, much worse for the curves here. Okay, so this comes from the understanding orbital integral, and then cosmologically this was found by a connection was found by Decatado, also Migrolini, who suggested we look at the cosmological shadow of the decomposition. So decomposition theorem can be thought of as a relative cosmology, but we can consider the cosmological shadow by taking the pk. So the cosmological shadow of the decomposition theorem actually is a filtration of the singular cosmology. So this is given by by definition we take. So you know this is so the cohomology, just write it down. That's a line. So the cohomology of the M and D can be thought of as the hypercohomology of Bn, taking coefficient in the FD lower star Q bar. Sorry, the Q the triple sheaf. So then, by looking at the contribution of different summons, the decomposition theorem, you get a filtration of the singular cohomology. So this is so it's the cohomology of the Bn, and you collect the first few summons in the right hand side by bounded by K, and yes. Maybe with a shift. So the decomposition theorem says that this complex can be written as a bunch of shifted perverse sheaves. And I only considered that for every step, we consider the information given by the first K summons, K minus one, K plus one summons. And this gives you increasing filtration of the singular cohomology here. So the reason here we consider decomposition and here we consider only filtration is because the decomposition theorem is not canonical. So this is not canonical. And so the best information we can obtain from non-canonical decomposition is that a filtration which is induced by the perverse truncation. Okay, so this is the cosmological shadow, which is a filtration on the singular cohomology. And the Decatado, Halzo, Migrolini discovered that this filtration detects the mixed Hodge structure of character variety. Yeah, so-called non-abelian Hodge theorem. Let me just write this down. Hodge theory, which is this P equals W phenomenon. More precisely, so you have you have the model of Higgs bundles, which is M and D. And if you forget about the algebraic structure of it, by remembering only the underlying topological space, this is actually can be identified with a character variety associated with the pi1 representation into the GLN. So this is a character variety, which is fine. And then furthermore, they predicted under this correspondence, then since both these two sides can be thought of as the same the different algebraic structure put on the same topological manifold, then you can identify their singular cohomology and the perverse filtration, which describes the complexity of the Hitchin system. On the other side, is given by the weight filtration associated with the mixed Hodge structure. So W2K. So in other words, the complexity of the Hitchin system is matched with the complexity of the boundary of this affine right, intuitively. And then of course this is a theorem. So now due to the work in my joint work with Davesh Maulik, and also independently by Hodge, Mallet, Inetz, Schiffman, using different methods. Okay, so this tells us that the cohomological shadow so for example, once you can have this bridge connecting these two worlds, then you have the structures you can have for the cohomology of the character variety can give you some prediction for the cohomology of the Higgs modular space, in particular the perverse filtration. I will come back to this point. What actually this bridge tells you or predicts from the motivic perspective. Okay. Any questions so far?
What's P there? HID.
Oh, you mean the letter?
Yeah.
This is the perverse. The P stands for perverse. So thank you. This is a perverse cohomology. Thank you. All right. So okay. So this is the first part of the result, which concerns the decomposition theorem, the description of the decomposition theorem, and the implication, the application of it of its cohomological shadow of the decomposition theorem. Okay. So the second part is, let me mention briefly, is the Laffitte symmetry, which is again a very general result concerning any algebraic map. Laffitte symmetry. So here we have this a list of perverse sheaves going from 0 to twice the relative dimension, and then, but actually you don't really get that much information. That you only get half of this information because these perverse sheaves are symmetric with respect to the Laffitte operator. So to just record this, I use capital R to denote the relative dimension of the Hitchin vibration of M of F D, and pick eta to be a relative ample class, relative ample line bundle. Then the cut product with a power of eta actually identified these objects. For example, the H
Ample and where?
relative ample as M, relatively with respect to the Hitchin vibration.
Does this is some canonical way? Canonical relative?
Yes, essentially there's only one class. So the P in the GLN case, there's a Jacobian factor, Jacobi of the curve factor, but for PGL there's only one class. You can choose this one. Yeah, thanks. So then the cut product with respect to eta, but generally this is a very general result for any proper map. So pick any ample, then this gives a symmetry for this perverse cohomology. which kills the information from 2R plus 1 to R plus 1. So this is R plus 1. Okay. So this is exactly the Hodge lattice, relative Hodge lattice applied to the Hitchin system. So lastly, this is a very general result, and the decomposition theorem this is a very general result for any proper map. And then, but in the Hitchin system, these results actually says interesting special properties of the cohomology. Just let me say this quickly. So if you identify the cohomology of here and here, then the Hodge lattice tells you that the eta, the cut product with eta, induces a symmetry, a lattice symmetry of the associated gradient of the perverse filtration. And then, since for both sides the cohomology are the same, so then it says that you have the cut product with respect to the canonical classing H2 actually induce a symmetry with respect to weight filtration, a lattice type symmetry for the weight filtration on the character variety side, which is in general very curious, and this was originally conjectured by Hauser, Rodriguez, Villegas. They call this the curious Hodge lattice for character variety, because so a priori there's no reason that the weight filtration associated with mixed Hodge structure satisfy lattice symmetry. But then later this was proved before the P equals W by Anton Mallet, who proved this using a cell decomposition by establishing a careful study of the cell decomposition of the character variety. And this is a consequence of the P equals W, because I mean the symmetry here is matched exactly with the Hodge lattice symmetry on the other side. Okay, so the third property. So we see that so here we see that Hitchin base only depends on the n, the curve and the n. It's not dependent on D. And then we can ask how the relative cohomology depended on D. And the answer is it does not. So I was very surprised to see this actually at first glance when I learned this subject. I will explain the reason. So let me state the theorem. So the picture is that you have, if you consider two different D, then you have two Hitchin fibrations to the same base, Dn, which I write this as Fd and write this as Fd prime. So the theorem, this is a prediction of by Hauser. Thaddeus the first proved in the category of constructible sheaves by Grothendieck with Ziegler, and also then in the category of mixed Hodge modules in the joint work with Davesh Maulik, which is that if you care about the relative cohomology of the Hitchin fibrations for different D, they're the same. So as an over the base.
With the ring structure?
It's a very good question. The ring structures are also the same. You mean after, wait, okay, so the two ways to talk about ring structure. One is that you take the global cohomology and consider cut product there, and they are the same. Here's the proof. So because the cohomology of this one, you can move to the cohomology of this one, and here is a Galois conjugate. For different choice of, so the D here is reflected by a primitive root of unity. And for different two choices of D, they are Galois conjugate, which have the same cohomology. You pass back here. So you have to pass through the non-abelian Hodge correspondence, which is the first way to see it. But also for relatively, you can also, so you can consider the monoidal structure. So this object and together with the tensor, then I think this is still open. I believe there should be an isomorphism. It should be possible to make this decomposition theorem compatible with the cut product, but I don't know how to prove it. Yep. But this is a good question. If time permits, I will discuss this thing. Yeah, thanks. So the reason I say this is the result was surprising is because is the talk accurate?
Yes.
Okay.
Not quite, yes.
So okay, good news. Okay, so the theorem so remarks. So this theorem tells us immediately, yeah. Then, so the theorem tells us that if you could the singular cohomology of at least as a Q vector space, this is isomorphic to the singular cohomology of M and D prime. However, this kind of thing is not true for vector bundle model space. For modular of stable vector bundles. So if you consider a Riemann surface, you consider model of stable vector bundles of rank n degree, say degree 1 and rank n degree 2, where 1 and n is, for example, the rank is odd. Then the model of vector bundle, so it was known more than 50 years ago by Hodge and Seaman that the Beatty numbers are not the same in general. And however, so if you consider, you add the data of the Higgs field, then the cohomological structures are the same. And moreover, the decomposition theorem are the same. So this suggests that, so you see that if I draw the picture here, over the 0 point of the Hitchin base, then the space which corresponds to D has a component over 0, which is the modular of vector bundles. But you have some other component correcting it. On the other side, you have on the D prime space, you also have a modular space of vector bundles. So I just write a modular, I just write N and D. So N and D prime. But these two spaces are not the same even as topological spaces because they have different Beatty numbers. But then somehow this correction make the cohomology to be matched. And not in the strongest possible senses, as I will say. I will explain. Okay, so this is something very so a way to see this from the perspective of the character variety is that if you consider modular vector bundle, the other side is only a unitary character variety, which is not algebraic. So it's a real analytic manifold. So in particular, Galois conjugate, you cannot run this Galois conjugate argument here. But this is exactly but it turned out it's not true. So it's very delicate for in some sense the Hitchin model space behaves better than model of vector bundles, more classical model of vector bundles. Okay, so these are the three results I explained concerning the topology of the Hitchin system. It considers the decomposition theorem, the Laffer's symmetry, and finally the dependence on independence of D.
So your Laffer's symmetries look like increase, and your first one can combine two get a canonical. Look like you get a number from White's. You get a filtration P here. You apply Laffer's operator, you get the other half, right? And get in there.
Yeah. So the Laffer's tells you that you can. So you have increasing filtration on the cohomology, and the Laffer's tells you that if you take the graded associate graded of this filtration, then on the cohomology, then this is a symmetry. So but yeah. In other words, so if you consider these dimensions, then it's symmetric in the index R. Does it answer your question?
I try to understand how to make this canonical with the Laffer's operator. You have a
Oh no, I mean in general, the decomposition theorem is not. In any case, I think. Okay, so yeah, this is a very good question. So I think in general, the decomposition theorem is not canonical. So cohomologically, you can think of this as like, so decomposition is a universal way of saying that the spectral sequence degenerate E2. So that's by no means canonical, but there are attempts which you can use. You can, if you add an extra data of this eta, then you can make it canonical, or quite canonical, and the Lin give like three ways of splitting the perverse filtration using a choice of the relative ample. But in certain examples, these three can be different. So it's not really that canonical, but
three canonical way.
three canonical. then Mark de Catado added two more. Yeah, but I would like to think of the decomposition theorem as a universal degeneration of spectral sequence, so that it's not canonical in that sense. And then the best numerical data we can associate with this is the but this is actually a very good comment, because from so if we have a little more knowledge of the cohomology of the character variety, we'll see that the weight filtration here actually admits a canonical splitting, because this cohomology is of Hodge-Tate type. So you have the Hodge filtration actually will split naturally this decomposition. And then if you translate everything to the left-hand side, this suggests that this Hodge-Tate decomposition here will give you a canonical splitting of the perverse filtration, which looks like at the beginning the multiplication by n splitting of the abelian schemes. But here that there are much worse singular fibers. So this is even after this P equals W is proven, this is a mysterious phenomenon to me. So it suggests that these symmetries coming from the smooth fibers actually, in some sense, it is chronologically should be extended over this entire Hitchin base in some mysterious way, which okay, now I discussed the topological part, then let's move to the algebraic cycles to try to explain all this phenomenon better. Of course, not everything can be understood via algebraic cycles, because first of all, non-abelian Hodge is highly transcendental, which is so this, of course, everything which you move from the things from the Higgs modular spaces to character varieties, then this kind of connection cannot be seen directly motivically, because this match is highly transcendental. But if you focus on one side of the story, and then I will explain, and there are ways to make it motivic. So the offshoot is at the 1, 2, 3, as I mentioned above, are all governed by algebraic cycles. And by the end of today's talk, I will tell you what the algebraic cycles come from. And it's not hard to imagine, as I commented at the beginning, that they should come from the Fourier-Mukai transform. Okay, so this everything I stated in the following are contained in my joint work with Davesh and Qizheng in 2 papers. One is last year and one is this year. Okay, so the theorem. So I will use the same number. So the theorem 1 corresponds to the previous topological part. The first result, the topological part. So I use R to denote the relative dimension again of the Hitchin system. So the first part is that the decomposition theorem, the BBDG decomposition theorem is indeed motivic in this setting. So there are motives which tells you which gives you the decomposition of the push-pull complex. So let me just say in motive-free language. So there exists a decomposition of the relative diagonal Bn into projectors. So pi 0, pi 1, in pi 2r. So this is a decomposition of the diagonal in the relative Chow group. So dimension So this dimension is the same as dimension of the relative diagonal, which is m cross m over b. So I omit this n and d here just for notational convenience. So there exists a decomposition of the relative diagonal in the Chow group such that this pi I are projectors. So this pi I, if you take the convolution product of two correspondences, the composition of two correspondences, this is either 0 or if I is not equal to j, this is 0. If I is equal to j, this is exactly itself. So delta ij and pi. And then moreover, this decomposition inducing the decomposition theorem. I from 0 to R, exactly the same index, I. Okay, let me explain first what's the meaning of this sentence. So you have a relative decomposition of diagonal, and this condition tells you that these pi I are orthogonal projectors. So pi I composed with itself is pi I composed with pi j is 0. Then you can use the relative diagonal to act on the push forward complex, which of course is identity. And then each projector will project into the corresponding perverse segment. So really this decomposition, each projection of the decomposition is realized by an algebraic cycle. And this is generally it's a wide open conjecture by Koti Hanamura, which is called motivic decomposition conjecture. Okay, so this is the motivicality of the decomposition theorem, and
when you say in general, so in what setting are they predicting the existence of these projectors?
Arbitrary proper morphisms. So yeah, I'll comment on that.
We need some smoothness.
So they have some proposal for the intersection Chow motives, and then even expect things to be true in that generality, but yeah, okay. So let me first finish. So first of all, you can construct the projectors, and moreover, these pi k are concrete. So the projectors, these pi k are essentially given by Arinking's Fourier-Mukai transform. Arinking's Fourier-Mukai transform for competitive vector covariance. Okay, so two remarks. The one is that, so first, this theorem says that you have a decomposition. The decomposition theorem has a motivic lifting where the projectors are given by some natural universal object. And the first, let me describe two remarks here. The first is that, so the part A confirms Koti Hanamura motivic decomposition conjecture. For the Hitchin system. So Koti Hanamura predicted that for any the decomposition, so any decomposition theorem should be lifted motivically, and this is a wide open conjecture. For example, if we just focus on the special case where the base is a point, we consider a projective variety, smooth projective variety to a point, and then the special case of this conjecture is exactly Moore's conjecture, which says the existence of Chow-Quinis decomposition. It says the decomposition of the diagonal, the Quinis decomposition of diagonal is motivic. lifted by algebraic cycle. In higher dimension, there's very few evidences in general. And now then Hodge suggests that okay, so if you have a family with singular fibers, then of course on the level of the topological level, you have to involve the perversity structure and do the intermediate extensions, this kind of thing. And all the complexity of these things should be measured by algebraic cycles. To the best of my knowledge, this is the first example where, as I will probably mention later, where the fiber topology of the fibers and the supports are very complicated. So yeah, there are not many examples known for this conjecture previously. And this concerns part A. And part B tells us that this pi k actually are of very concrete forms. So this pi k is actually it helps us to see two structures. One is that by part A, this pi k detects the perverse filtration because they are projectors lived in the decomposition theorem. So the pi k will detect the perverse filtration. And by part B, this pi k can be written in terms of certain universal object. The pi k also can detect the tautological classes. In other words, use this projector. This gives you a proof of P equals W conjecture, which is different with.
The second part is the universal. Is still something like a Poincare bundle.
Yes, not bundle. It's a Poincare. So it's a Poincare sheaf.
Some canonical sheaf and the product of the
yes.
of Jacobian, compatible Jacobian.
Yes, for the compatible Jacobian associated with integral curves, there's a Poincare sheaf where you can construct cycles. And then finally, for the Hitchin system, because you have more complicated curves than spectral curves than the integral ones.
Anyway, generalization of Poincare bundle.
I can generalize this to certain compatible Jacobians, and these are the cycles we use actually. Yes.
And what I say is in the classical case of Jacobian of smooth curve, is that just a Poincare bundle?
That's exactly Poincare bundle, but after extending, it's no longer bundle. It's
something
complicated. Yes, that's correct. Thanks. Okay, so maybe let me say the results, and then let me just say one word about a few words about proof, and if you're interested, we can talk afterwards.
So you can prove Hodge lectures by this.
I will state it.
I must state it.
Okay, the second theorem is that the Lefschetz standard conjecture is also true for Hitchin system. Theorem 2. Lefschetz standard conjecture is true for FD. Namely, there exists a cycle which depends on eta, the relative ample, and I in the relative Chow in the relative Chow group, such that this correspondence on the decomposition theorem is the same as the cup product with I in the inverse. Which forward of context. So in other words, the inverse of the Lefschetz operator is motivic. Well, lastly, actually, the last part is also simple to state because it exactly says that the motivic decomposition of A is D-independent. So which means that the relative cohomology of different Ds are matched in the strongest possible sense. Sorry, this is wrong. So it's not a strong the additive structure, but also you can consider cup product, and that part is still missing. The theorem switch. That motivic decomposition obtained in 1, the theorem 1 is D-independent. Although the geometry of the fibrations are very different, but the motifs you constructed from it are D-independent. Okay, so that's the result, and the proof basic. So you have to find out what are the algebraic cycles that detects the complexity of the singular fibers, and to match with this perversity structure happen over the singular fibers. And it turned out that the Arrinkin's extension of the Fourier-Mukai transform, which comes from the left-hand side of the diagram I drew at the beginning of the talk, that's exactly the correct thing. So the Fourier-Mukai transform tells you that what's the right thing to extend in a coherent world, and this actually is matched with the extension which happened in the constructible world. Okay, I'm stopping here. Thanks.
For the classical modules with the regular bundle, this not be true, right?
Even the weighting numbers are
not
different.
known.
Which is not known.
You talk Higgs bundle, right? For classical vector bundle.
For classical vector bundle, depending on what statement you want. So you know that the motive is abelian, so this, so it can be. Yeah, for that I think the motive that one is easier. So because you can decompose the motive, you can write this motive in terms of the curve, and the line curve, either the symmetric product and the Jacobians. So this is known. So here the harder thing is the relative geometry. Because so far it is not very well understood what are the topology of the singular fibers of the Hitchin vibration. So that's also the reason that even the decomposition theorem, which after in Gold was studied intensively by many people, Chadua, Lomon, Tecatado, Migrolini, Hanov, but so far I don't think, for example, even the supports is as fully described due to actually the complexity of the Hitchin fiber. So every time when we work on these things, we have, so basically the idea is to avoid controlling the worst Hitchin fibers and try to find some clever argument to avoid doing that. So yeah.
Sorry, what is the meaning of the last statement? What motives are D-independent?
Okay, so if I write the relative motives HI to define this to be a morphic, so a variety over the, this is a variety over the.
So like the ith cohomology motive of FND.
Yeah, this is pi I, maybe some index, and this motive is isomorphic to the corresponding motive for d prime. So yeah, so the decompositions are matched in the stronger sense. And the isomorphism is constructed explicitly by some algebraic cycle. So
you have find the correspondence.
Find the correspondence. So it's ND and ND prime and D prime, and so basically you want to construct enough algebraic cycles on this relative product to give you the isomorphism. This is that's what it means.
Can you say something more about the construction of the projectors? What's actually happening on the console?
That's a very good question, and this is the key part. So there are two parts. Let me do this quickly. So there are two parts. One is that you deal with basically the compactified Jacobian. So the first part is to deal with the compactified Jacobian associated with this integral locally planar curve. Which does not govern the entire Hitchin system because there are worse curves. And the step two is to use Springer theory. Springer theory to pass to that, to reduce to one. Okay, so this part, as I explained at the beginning, not beginning, but as I explained. So on this singular relative product, so you have, so this is a very singular space in general, but if remove one of the bar just by considering J cross J bar over B, then the Poincare line bundle actually is defined here. The Poincare can be defined as this is an open subset with boundary of codimension 2. So then Arinkin showed that there is a maximum Kolmogorov sheaf given by extending this line bundle, and then the characteristic classes of this P can be made to form these projectors. But the formula is complicated. We can talk afterwards.
For the classical modular, classical vector bundles is leaving the singular fiber, right? So
Right.
Yes.
so for this theory, you have to push forward some way for this transform to work.
Oh, you mean
If you want to say something about classical modular space vector bundle, then
you could put this in the family, and you know that relatively there are all these things work. But if you want to restrict it, so to that model vector bundle and say precisely, for example, what happens there, I don't. So there are two different ways to think about Higgs modular space. One is to use the Hitchin vibration, which is the way we took here. Another is to use the Bielinsky-Birula decomposition of the C star action, the GM action, which you can decompose your. So you have a GM action which acts on a Higgs field. So you have one of the fixed locus as the classical modular space, and then you have a correction terms. So I don't think I understood completely that. So you see that this is deep independent, but this is not, meaning that these correction terms will, in some sense, compensate for different Ds. But I cannot write down a formula concretely here what happens. But then so this is the GM direction, but also you use the Hitchin vibration direction to actually compare these spaces for different D. So that's an interesting question. What happens when you match the Hitchin modular spaces for different D, and what happens for that component? For example, is there the formula for that, which I do not know.
I was a bit confused when you say the decomposition is not canonical, but somehow the projectors are.
Yeah, this is just one of the ways for constructing the projectors. So sorry. After constructing the projectors, this gives you one decomposition, but there might be others. Sorry.
but that decomposition is unique, right? It's canonical.
Well, after writing down this, then it's unique.
But you have one explicit way anyway. It doesn't depend on this requirement, right? The requirement
That's true.
says induce one decomposition. Maybe one says something like that.
Yes, inducing
One decomposition.
this. After you write this down, then this is a canonical.
Wait, so if you ran this up, like since you have I don't know how much control you lose in step 2, but presumably you have some explicit control on the denominators that show up in the pi i's.
The denominator. You want to make things more integral, or
I want to write down some integrals. Like for example, I want to know what are the primes for which there's a decomposition theorem with mod p coefficients.
oh. Okay. Even in the abelian. In the abelian scheme case without singular fiber, then this is the k factorial, right? So this is Chen character of a line bundle, which is k factorial. But now it's not a line bundle; it's just some Kolmogorov sheaf. So then, in order to take characteristic classes, one has to use like the photons. For example, one has to go use things in, for example, Photons book chapter 18, like localize the Chen classes to get cycles from it, and I do not know if there is. I don't know if there is a way to control the denominator. It's a very interesting question. I don't know. I even do not know how to bound it.
Any other questions?
Again, no questions. Let's think.